Hi there, my name is Vivek Subramanian. Today we're going to look at equivalence examples.
Hi, I'm Michelle Maharbiz. Let's get started. So the first example wherein we want to use some of these equivalent circuits is in a canonical little thing everyone does in these courses called the maximum power transfer value for the load resistance. So it's pretty easy to explain why we might want to do this. There's a lot of cases where you'll have an electrical circuit and you'll want to connect it to another one. So for example, let's say that the electrical circuit that's producing some power is here on the left. And I'm going to connect it to some sort of load. And what I'm concerned with, you can imagine right away that this would be a concern, is that I get the maximum power transferred to the load. So first off, we already know that to the left of these two terminals, that circuit might be a very complex linear circuit, but we can model it using the Thevenin and Norton theorems by an equivalent of a source and a resistor. So here we've got our Thevenin voltage source in series with our Thevenin resistor. So to the left, it could be anything. As long as it's a linear circuit, we could represent it this way. To the right, likewise, we might have something somewhat complex, but we will represent it with a load resistance. As a quick example, when we do op amps very, very soon, you'll see that if I look into the input terminals of the op amp, I can, to first order, sort of think of that as looking like a resistor. So now I'm worried about what is the maximum power transfer going to this load resistor. Another great example is a battery running a motor. So you know that a realistic power source, a voltage source, like a battery, is going to have some internal resistance, right? We spoke about this several times. It models the losses and so on. And the motor can be represented, for our purposes today, as a resistor. They're a bit more complex. They include other components, but we'll talk about that later. So now, the very basic question. What is the best load resistance given the equivalent circuit on the left? Given VTH and RTH, what should our L be to get maximum power transfer? Okay? So we've already said that no matter how complicated these things are, they can look like this circuit for the purposes of this little problem we're about to do. So the general procedure is fairly straightforward. Okay? What you want to do is come up with an expression for the power through this load, and then we want to ask the question, what's the optimal value as a function of this load resistance? Well, what we're saying is that we're looking for a maximum or a minimum power as a function of the load resistor. We can remember our sort of math background, and we can take the derivative of the power, the load power on this resistor, with respect to the load resistance. And if we take the derivative and set it equal to 0, we'll be solving for places where the power gives you a maximum or a minimum, right? And then we would have to do a second derivative test to make sure it's actually a peak, right? Could be a minimum. So let's follow that thought. So what is the power being consumed by the load? It's the current through the load squared times the value of the load, right? Pretty easy. And of course, what's the current going down the load? Well, there's only one current going around this loop, and that current is the Thevenin voltage divided by the sum of the resistors, right? V equals IR, where these two resistors form a series equivalent resistor.
So you just did a KVL there to figure out.
Yeah, that's all we did. KVL around the loop, only one current. And so I substitute that in, and you can see that the load power is going to be the Thevenin voltage divided by the load plus internal resistance squared, right, times the load. And now we'll do exactly what I sketched out. If I take the derivative of this expression, right, this is the function power through the load, which is a function of the load resistor, I can take the derivative of this. So by the way, just to overdo this a little bit, imagine this equals y and x is my r sub L. So I can take the derivative, right, dy dx. It's basically taking the derivative of power. I'm asking how the power changes as a function of how the resistor changes. So I take this derivative. You can do it by parts. I'm going to let you all do it, but you can see RL is in the denominator here, and it's also here. So I can do it in two parts, where this, because it's multiplied by RL, will show up in the first part minus, and then, or rather plus, you'll just get a negative when you take the derivative with respect to the part down here. So you see it's pretty straightforward. You get to the third power here and a quadratic there. Now what we're going to do is set it equal to 0. Remember, because we want to find places where there's a maximum or a minimum, right? In the derivative, when the derivative sort of flattens out at a maximum or a minimum, the derivative will equal to 0, right? It'll be horizontal. Make sure you remember that from your math. Anyway, once we set it to 0 and clean up a little bit, we're going to find that the load plus the Thevenin resistor equals twice the load. And obviously, just by observation, bringing that over and cleaning up, it tells you something pretty interesting, which is that the load resistor has to be the same value as the Thevenin resistor for there to be maximum power transfer to the load.
So what you've given here is one value. You've given me one case where you said this condition is true, namely RL plus RTH is equal to 2RL. You gave me that condition is true when RL is equal to RTH. That could also approximately be true if RL was infinity, right? Because if RL was infinity, 2 times infinity is still infinity, and you'll say the left-hand side is approximately equal to the right-hand side.
Well, but so as RL goes to infinity, what happens to the current through your thing?
We get to the minimum power transfer.
There you go.
So we're left with what you're saying is this condition therefore necessarily represents the maximum power transfer.
Right. So another way to look at that is to basically do this second derivative test, which I sneakily avoided. But you could take a second derivative and you'd find exactly what you suggested, that one of these is obviously the maximum, and then you get the minimum where you get 0 current because the RL went to infinity. Good point.
Got it.
Yep. And so this is called the Thevenin, the optimum load resistance is sometimes said to be matched when this occurs. Okay? And by the way, as a preview, we're going to see this again when we make our loads more complex, when we make them impedances, which is to say when capacitors or inductors get into the picture, we're going to revisit this, and it'll follow the same sketch, but once inductors and capacitors are in there, it'll be a little more interesting, and we'll give you all sorts of applications in microwave circuits and antennas and so on, where the same notion comes up. So last thing I want to say before we move on is that this really finds its use in many, many places, not just say, how to get the maximum actual, power from a motor to a battery. In its more complex form, it finds its way into all sorts of radio frequency and antenna and communication applications. It's a really simple but fairly fundamental thing.
And one example where actually even in the DC sense it matters is, for example, if you have a photovoltaic panel, a solar cell array on the roof of your house, there's an inverter there that takes the DC output of the solar cell array and drives it into the grid. To maximize the efficiency of that system, the inverter is often designed, and here the inverter would be the RL. The inverter is designed such that you get maximum power transfer from the solar cell, which would look like this, into what ultimately gets put into the grid.
Huh, I didn't know that. My suspicion is that your roof is covered with solar cells.
It is.
Okay, so let's get, what else is up? What are we going to do next?
All right, so let's move on now. Let's talk about another example that we often use in this study, and this example is called the Wheatstone bridge. So Wheatstone bridge is shown right here. A Wheatstone bridge fundamentally consists of a diamond-like network of resistors. So we have these 4 resistors, R1, R2, R3, and R4. And at the intermediate nodes, so the node points between R1 and R2 and between R3 and Rx respectively, we can measure the voltage between them. Or we could measure the current that will flow between those nodes. So in this case, I've given you R1, R2, R3, and a 4th resistor, which I'm going to call Rx right now. The reason I'm going to call it Rx is I'm going to say that's an unknown resistor. So I know the values of R1, R2, and R3, but I don't know the value of Rx.
So let me try to think about this. So I'm sure you're going to work through the math in a minute, but let's say, I guess where this would be useful is if, for example, if there was a sensor that changes resistance as a function of something I'm measuring, like maybe temperature or maybe mechanical deformation or something. And what you're saying is a really good way of measuring how that thing is changing is to embed it in this bigger circuit with these 3 other resistors and measure this little VG maybe.
That's right.
Okay.
So a classic example is one of the most common resistor sensors that has a value of resistance that changes with what it's sensing is, of course, a thermistor, which measures the effective temperature.
Oh, I see. Okay.
So you can have a resistor. Its resistance may change as a function of temperature. You can stick it into this circuit, and now you can figure out the temperature because you can use this circuit to figure out the resistance. And then if you know the resistance, you know the temperature.
Got it.
Now, the way we do that is we essentially will have known values of R1, R2, and R3. And in particular, what you're going to find is these values, if we can change them in known ways, we find the point at which the voltage between these two nodes labeled plus and minus is 0, or equivalently, we find the point, if we were to put a current meter, a galvanometer here, where we measure it such that there is no current flow between these points, in other words, there's no voltage drop, we will then be at a point where we will have a fixed relationship between R1, R3, R2, and Rx. And so if we know R1, R3, and R2, we will then know Rx.
All right, I sort of get it, but let's see. Let's do the math.
Okay, so I'm going to give you an example to work through this. So here's what we've got. I've now taken that Wheatstone bridge, and I've got known resistors, R1, R3, R2, and I have an unknown resistor, Rx. And let's say R1 and R3 are fixed and known, and R2 is known, but I get to pick what value is there.
Oh, I see.
All right, so I'm trying to figure out the value of Rx, and I'm going to adjust R2 till I find that there's no voltage drop across these terminals.
Okay.
Then if I know R2, it turns out I'm going to know Rx. And the way I'm going to do that is I'm going to take advantage of what VG is defined as. So you'll agree with me that VG is the voltage difference between the plus terminal and the minus terminal.
Yeah, that makes sense.
All right. So first, Michelle, what is the voltage of the plus terminal? Let's ignore the right-hand side. Just focus on R1 and R2. What's the voltage on the plus terminal?
So if I do a KVL that starts from that battery on the left and swoops clockwise down through R1, then through R2, and then back to the battery, and I know that in the case where no current is flowing through the VG branch, right?
Right.
Because I'm measuring it, then it's just a voltage divider. So I guess it's R2 divided by the sum of R1 and R2 times the battery, the V in voltage. Is that right?
That's right.
Okay.
So if you look over here, the first term in this equation, which is the plus, is R2 over R1 plus R2 times Vn.
Okay.
Now, of course, VG is defined as the voltage of the plus minus voltage of the minus. We would do the same thing on the minus side, and we'll get Rx divided by R3 plus Rx times Vn. And VG is therefore going to be voltage at plus minus voltage at minus.
Okay.
So that says VG is just equal to R2 over R1 plus R2 minus Rx over R3 plus Rx times Vn.
Oh, let me see if I see where you're going. So there's almost like two ways to try to find what the Rx value is. One is to measure the voltage difference between those two terminals.
Right.
Right? And if Rx is equal to, we know R1 and R3 are the same.
Right.
So when Rx is equal to R2, we'll have no voltage difference across them.
Correct.
Right? And moreover, if Rx is different from R2 and I measure VG, I'll get a value, but I can figure out what Rx must be for that value.
That's
so
right.
basically, if I measure VG, if say my little instrument measures VG, I'd be able to figure out what Rx is. But the other thing you're saying maybe is a different tack to take. I'm sure that you're going to tell me they're related, but I guess the other way to do it is to mess with R2 until the current going from left to right, if we had a branch that would equal 0.
That's right. I would go one step further. So here's the key point. It turns out it's harder to make really good voltage measurement devices than it is to make a really sensitive device called a galvanometer, which detects current. And the galvanometer is kind of interesting because we can make a really good one that'll be very sensitive to current, and it'll tell us is current flowing from left to right or right to left.
I got it.
So there's two ways of doing it. One is you could measure the voltage and then figure out Rx, which was the first thing you talked about.
Right.
But I've told you we don't have really good voltage measurement devices.
Got it.
The other way to do it would be to not try to measure the voltage. We just try to adjust R2 till we get to no current flow.
Okay.
And when we get to no current flow, we then know, assuming R1 and R3 are equal, that would indicate that R2 and Rx are equal.
Okay.
Okay? And so under this balanced condition, there'll be no current flow. And then we can say, if we know the value of R2 and R1 and R3, we then know the value of Rx.
Got it. And
So-
I see.
That's the basic idea in the Wheatstone bridge.
And that's what you got it written at the bottom. Perfect. Okay, that makes sense to me. Okay. So let's do our third and final example of the use of equivalent circuits in say a useful device. So here we've got a BJT. This is essentially going to be our very first transistor or three-terminal device that we'll look at in this class. BJTs are very common in analog circuits. They used to be common in the up to about the late 70s, early 80s in digital electronics, in mainstream sort of processors you might buy from Intel. And the nice thing about the BJT is that we'll be able to give you a pretty straightforward equivalent circuit for what is otherwise a very weird device to you probably for large DC signals. So the goal of the next 3 slides is to give you an example of you can take something like this, which you're probably while I'm talking staring at these things and not sure what the heck what is going on in these devices if you've never seen them before. And we can say, in the case where we have fairly large DC potentials, we're not worried about very small oscillations or strange things, we can give you a pretty nice equivalent circuit for this that you could plug into any other linear circuit and use it to solve what the state of this transistor might be. And we'll find uses for this. It's not just a toy example.
So, Michel, you said that these were used in microprocessors in the 70s and early 80s. To give a little historical note, we used to call those devices TTL devices for transistor-transistor logic. Now, here's the reason I mentioned that. You have those USB sticks that you use as memory sticks.
That's right.
And you know that some of them, and for example, solid-state drives as well, operate at 5 volts. Which is a weird voltage when you think about it.
That's
because
true.
You can't get a 5-volt battery.
Right.
You can get a 1.5-volt battery or a 3-volt battery. Why would we have a 5-volt supply standard?
I never thought about that.
Yep. The reason is because TTL, for various reasons, used to use a 5-volt standard. So because of that, because of these bipolar transistors, we developed this 5-volt standard, and that has survived till today.
Oh, that's really interesting. So, by the way, I guess we haven't told them what BJT stands for, which is bipolar junction transistor. So let's just start by just looking at it, right? And so here's the first thing I'll tell you. First thing you need to know is there are 2 flavors of these. They operate, obviously very similarly, and in some cases are almost duals or inverses of each other. We're not going to get into too much detail about these differences for now. Suffice it to say that in the courses following this, you'd run into the physics of the differences between them.
So to give you just a little bit of background here, you see those things labeled N, P, and N? Well, those are, that entire stack is a block of semiconductor material. For example, it could be silicon or germanium or gallium arsenide, what have you. And each of those is a region within the material that is designed to conduct in a particular species more dominantly. So, for example, N will have an excess of electrons, and the electrons will tend to be the dominant conductor within it. P has absence of electrons, and so it turns out effectively there's a net positive charge because there's an absence of electrons that becomes the dominant conductor. You don't need to worry about how we went about building that for now. Later in the course, we might give you a little bit of an overview. But really, right now, just accept that we are able to build devices. Now, you heard the term bipolar junction transistor. And we use the term junction to describe an interface between, for example, the N and the P. And so you see that we have 2 junctions here, one from the P to the N, and another from the N to the P. And so we call it bipolar junction transistor.
There you go. And so basically these transistors are constructed by bringing together 2 pieces, say the P and the P down here, sandwiching another one, this N type in the case of the PNP, and it leaves 2 interfaces behind. And so by electrically contacting a wire to the P side at the top, we'll call that the collector, and putting another wire to the bottom, we'll call this the emitter, and then again, for the 3rd region, we'll put a wire connecting to that. We'll call that the base. Base, collector, emitter. Okay? That's what B, C, and E stand for in this. Now, we don't know yet what this does. We just know that I can connect 3 wires to these 3 regions, and something semi-magical maybe happens in between. But what we can do, just logic really, is we can define currents and voltages between all of these terminals. And I'm not going to sit there and read every single one, but you can see that we've decided on polarities and directions of currents. This is called the base current, I sub B, going into the base. Likewise, there's a current I sub C that goes into the collector, and a current I sub E that comes out of the emitter, and voltages associated between the base and the collector, the base and the emitter, and the collector and the emitter.
So, Michel, if I remember what we learned some time ago about KCLs, I'm assuming that if I were to draw a box around that bipolar transistor, IC plus IB should equal to IE because of the way you've drawn those arrows?
Yeah, that's right. IB plus IC coming in must equal IE coming out because, you know, there's certainly no other place they're going, and we're assuming that nothing in here is charging up for the purposes of our, remember, DC signals. So we're making it pretty easy on everybody. Yeah, that's absolutely right. You're kind of getting ahead of ourselves. So now, last thing I'll say, we've sort of made this long, but what are these things good for even before we tell you how they work? You know transistors are used in a lot of things. They're certainly used for amplification and gain and for changing sort of input-output characteristics. You'll see what we mean by that as the course goes on, and we'll give you a taste of that right now.
Okay. So whenever we work with these sorts of active components, and we call these active components because they do these sorts of things like gain and amplification and switching, etc., we often would like to replace them in our schematics with simpler components that we know how to deal with. And we call those equivalent circuits. So let's start by looking at an arbitrary transistor circuit I've set up. So this is the BJT. You'll recognize this as an NPN BJT from the previous slides. And I've set it up with its terminals connected in the following way. I've got the emitter connected to my reference node, which I'll call ground. So it's the bottom of this battery over here and the bottom of this battery over here.
Oh, okay. Convenient.
Yeah, so I'm going to call that my reference node. Michelle, why did I choose to make this my reference node?
My guess is because there's a lot of branches going into that node, and it happens to be at the negative terminal of both those batteries.
That's right. Those rules, we actually do live by those rules that we give you.
Okay.
All right. Then what I've done is on the base, I've connected it to a battery which I've called VBB, and I've put a resistor between the battery and the base. So what that means is it looks like I have some sort of loop over here, but I don't know how to deal with this. Right? That's the base emitter junction. I haven't figured out how to deal with that yet. And then for the collector, I've done something similar. I have VCC and an RC, and then I've got another loop over here between the collector and emitter. I don't know how to deal with that yet.
So when I was first learning this, I always thought that was weird. I got the left side. You know, there's an equivalent circuit there, BBB and RB, which is like an input source. It could be anything, a battery or anything providing some input voltage. But then I thought, well, wait, that's weird. Then they're sticking another battery on the output. Isn't the output supposed to produce a signal? But I guess if you're a student out there, just bear with us for another minute and a half, and you'll see the reason why we apply that little voltage at the output.
Right. So let's talk about that briefly. You know, you're thinking, intuitively, you're thinking, well, this is an amplifier that should give me more voltage. But this device is not capable of making its own energy. So it'll give you a boost in voltage, but it does it by taking energy from another source.
Right. So you're right. That's exactly why VCC will show up. But let's go through the equivalent circuit.
All right. So let's look at an equivalent circuit. So it turns out the equivalent circuit, the simplest equivalent circuit for a BJT. So I'm going to replace just what I show between the B, C, and E nodes is what's shown here between the B, C, and E nodes. In other words, the simplest equivalent circuit for a BJT is between the base and emitter, we represent it by a voltage drop, a VBE. So it's like having a battery effectively internal to the system. It's a special battery in that you cannot draw energy out of it, but think of it as a voltage drop. Okay? And then between the collector and emitter, we represent it as a constant current source. But it's a special type of constant current source. It's a current-controlled current source. So it's a dependent source. And it turns out the function that describes it is beta, some number, times the current IB. And beta, therefore, in a sense, represents current amplification. So think of this BJT as a device that amplifies the current going into the base by some value beta and makes that current show up at the collector.
Okay, so let me go through this. So first thing you're saying is that whatever current we manage to force into the base is going to be replicated and multiplied by beta, and that's going to show up going into the collector.
Exactly.
Okay, and we haven't violated the collector plus base current equals emitter current because conveniently we have ground at the emitter, and so KCL is fine. Obviously, those two currents, IB and IC, together form the current going down into ground.
That's right. So you can actually see that here. where you see that IB goes into the emitter and IC goes into the emitter. So it's going to still work because IE is going to be the sum of IB and IC.
Right. The other thing that always weirded me out when I was a student is you go from the top diagram, which has almost like a Y, right? You have one coming in and then one coming in at the top and the emitter coming out. And then in the bottom equivalent circuit, we've sort of split the branches so that they look like they're coming in two separate paths to the emitter. But of course, all of the bottom wires are all shorted together, so it's exactly the same as the top. And I always get this question, too, from students. It's kind of weird that we've separated it. But the thing to remember for the large signal model is the two things Vivek said. One is you're always going to present a voltage drop between B and E to whatever your input circuit is. That's essentially what this is doing. It's always presenting a little bit of a drop. And then the collector current is going to be beta times the base current. Okay? So if you remember that, we can actually talk about this circuit pretty easily. So let me take a stab at it.
Sounds good.
Okay, so what you're saying is, first of all, if I want to figure out what the transistor is doing at the output, I have to figure out the base current.
Exactly.
Okay, so but the base current's not that hard because I have one single little loop I can do KVL around.
That's right.
So what I'm basically going to say is that VBB minus VBE is the voltage across this resistor, right?
That's right.
So that voltage, VBB minus VBE divided by RB, by Ohm's law, gives me I sub base.
Exactly.
Okay, so I sub base is going to be set by the input source, its resistance, and then the little drop that the transistor forces on the input. Okay, so I can solve that.
All right.
Then I'm going to take that, and I'm going to multiply it by beta. Now, what's the typical value of beta for a real transistor?
It varies, but modern transistors will typically have betas well over 100. It's quite common to have betas of 200 to 300. In fact, even more than that is possible. Okay.
So what you're saying is this is going to go, maybe, let's just say a milliamp was being fed to the input. You're talking about, a reasonable fraction, a tenth of an amp kind of coming out the output.
It could be 100 milliamps, a couple of 100 milliamps. It depends on the beta.
Right. Okay. And so so now I've got beta times, VBB minus VBE over RB is going down the collector. Okay. And so, wait, how do I figure out VCE if I know that's the current? I guess, well, let's assume nothing's connected to the output for now, right? Which means that all of the current IC going down must equal the current kind of going up this branch, right?
Exactly.
By KCL. And so if this current is going up, I know the voltage drop on the resistor must be IC times RC.
Exactly. So now you know VCE.
Ah, that's right, by KVL on the right side. VCC minus RC times IC must equal VCE.
Yep. Do you want to try to actually work it formally?
Sure.
All right, go ahead. Okay. So, Michelle, why don't you start working through this, and I'll jump in, and we'll work through this together.
Oh, okay. So now what you're saying is, okay. So now that we kind of figured it out, we're gonna do it as a digital inverter. So kind of see how maybe it gives us an inverter.
That's right.
Okay.
Now, before we do that, I want to place some rules. It turns out you don't get the beta all the time. Okay? So I'm going to give you some rules for now to force you into a regime where it's going to work. Okay? So I'm going to tell you that V out cannot exceed VCC. Okay? What that basically means is I cannot be pouring power into the battery. Okay? So I'm going to lock you into a configuration where V out cannot exceed VCC, and I've picked 5 volts. And V in, I'm going to tell you, is going to be positive. I'm going to make sure it's not negative. Okay? And for now, just trust that I'm making you do that for a reason. It turns out the reason I'm making you do that is going to ensure we are in a place where we can use our beta formalism.
So this is an example we were talking about earlier, right? That you can linearize a nonlinear circuit and come up with an equivalent, but there are certain constraints on that linearization.
Exactly.
It's only going to be good for some operating conditions.
Right. I've picked the conditions such that you can work with the equivalent circuit I've given you earlier.
Okay. So what we're doing, let's look at the circuit. We've got a BJT. We've got a VN voltage we're going to supply to it from somewhere else. We've got a base resistor of 20 kilo ohms, and we've got our VCC as a 5-volt source and a 1 kilo ohm RC resistor. And I guess what we're looking for is to figure out what V out is as a function of VN.
Yep. So I'm going to guess the next thing we do is we draw an equivalent circuit.
Hey. That's correctly. You're pretty good at this.
It makes you think I must have known about what's in these slides.
Yeah, I think maybe you can make a career out of this, Vivek. All right. Anyway, so we're gonna stick in our equivalent circuit, and you see that Vivek has provided us with a beta of 200.
And you'll also notice that the VBE is 0.7 volts. That turns out to be a fairly fixed value for silicon. Okay, so if you make that value of VBE is to a large degree determined by the material of which your transistor is made. And for silicon, it's about 0.7 volts. For germanium, it's about 0.3. There's different values for different materials.
Okay. Without getting into details, I'm going to guess that there's a reason that this number is very similar to a PN junction diode forward voltage. Okay. So let's see. So we've got our equivalent circuit. So now I can, I guess, follow the rules I laid out in the last slide. My base current is going to be Vn minus 0.7 divided by 20K. My collector current is going to be beta times IB. So that's 200 times this expression up here. And my V out is going to be VCC, which is 5 volts, minus IC, 200 times IB, times RC.
And that's because that represents the drop across that 1K resistor.
That's right. This right here is the drop across the 1K resistor as we did. Okay? So putting that all together, V out equals VCC minus, and you can see we've substituted IB into IC and then IC into V out, and we get this expression right here. So my guess is we could plot this and see something interesting. So we've got V out as a function of V in. Everything else is known, the resistors, the betas, the VCC, and the built-in voltage drop. So let's take a look at this. So for V in that's very low, say 0, I put a 0 in here, right? And my VCC is 5 volts. So for 0 here and a fairly, let's see, what are these values? RC is going to be 1, and RB is 20K. So this is 1/20th times beta plus this little 0.7. Oh, but you said V out can't exceed 5 volts.
Exactly.
Oh, so basically what you're saying is V in is so low that it pushes it up to 5 volts, and then it just sort of flattens out there. That's what it's got to be 5 volts. It cannot exceed it.
Exactly. This equation framework that you have right here works because I'm assuming beta is 200. Well, it turns out beta is only 200 within certain bounds. Otherwise, you don't get the amplification you expect. So you get locked into a situation when you have very low input voltages. In fact, when you have input voltages that are less than 0.7 volts, you essentially have no current going, and your output gets locked at 5 volts.
There you go. So what happens for very large V-outs?
All right. So now for very large V-outs,
or V-ins, I'm sorry, very large
that's right.
V-ins.
For very large V-ins, we have massive amounts of IB, okay, because you've got, let's say, 5 volts in. You have 5 minus 0.7 divided by 20K. When you multiply that by 200, that would say you'd have a huge voltage drop across this 1K resistor, which in turn ought to pull this negative, which isn't allowed. Okay? So what happens is the output voltage cannot exceed 5 volts because that's set by the battery, and it cannot drop below 0 because, again, that's set by the battery. So the circuit only works within those bounds.
So, okay, so I see. So what you're saying is this V out equals, some function of V in describes this line right here.
Exactly.
And then it gets clipped off at the top and the bottom by these sort of rules we've made up. One of which it turns out we didn't explicitly write, which is that V out can't drop negative either.
Right.
But the point is, this is an example of where our linear circuit works well here, and here we have rules for dealing with it. But let's take a look. What does this look like to us? Well, to me, it looks like an inverter, something that takes a low voltage and produces a high voltage, or takes a high voltage and produces a low voltage.
Yeah, that's right. Now, so remember, you've probably learned at least briefly about Boolean logic in other parts of your life, assuming you're an engineer. And that being the case, you know of a function called inversion. And inversion basically says if you have a binary system where you've got two possible states, 0 and 1, an inverter will take an input of 0 and produce an output of 1, or take an input of 1 and produce an output of 0. And we represent inverters by this schematic, which you've probably seen before. So in fact, you've now built an inverter.
So let me guess a couple things. One is, my guess is that you could probably build more complex logic gates than this with BJTs, obviously.
That's right.
And that's probably what people were doing in the late 70s, early 80s, right?
That's right.
With the early Intel process.
That's right.
Okay. And the other thing I want to point out is that we've shown you an example with a digital inverter because it's a very simple example. But my guess is that you could use the same thing for analog amplification within certain constraints.
Yes, and in fact, I can point out how that is true. So think about what you've got in this region, in the sloped region over here. The input voltage is changing from about 0.7 to about 1.2 volts, and the output is changing from 0 to 5. So it looks like for small changes in input voltage, I'm able to produce large changes in output voltage. So at least in this region, it appears to be an amplifier.
Okay. So the last take-home message I've got is that the BJT is kind of a current amplifier, and we can use it that way, or we can set it up in a circuit that allows us to translate that current amplification into a voltage amplification.
That's right. And we've done that here by putting a resistor, which basically converts an input voltage into an input current.
That's pretty cool. All right. Well, we'll catch you guys next time, and see you soon.
Yep.